States of matter pre-quiz, blah, 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 whatever. This is all about how these solids are going to have different intermolecular forces and how we can figure out what their properties are going to be based on that. So first off, let's figure out what are the different intermolecular forces in these solids. So let's go ahead and write these down. So I've got CCl4, got SiC, got NH3, AlCl3, KCl, and He. Okay, so these are all of these different materials. Well, what kind of solid, what kind of intermolecular forces would CCl4 have? Well, it's going to look like, if I draw this out, carbon has 4 bonds, and all 4 of those are going to be taken up by chlorines. So this is going to be a molecular solid, and it's only going to have, let's see, London dispersion forces, LDFs. Okay, let's erase that, the label there. So let's say London dispersion forces, molecular. All right, then how about silicon and carbon? Well, both of these are going to have 4 available bonds. So even if each one triple bonded, I still have 1 bond left over. So obviously this is going to have to continue. So I could even have something like this, and it would just go over and over and over again. Okay, so then that's got to be a covalent network. Okay, so that's going to be covalent network. And it's going to be held together by covalent bonds. So if you tried to melt it, you would be melting covalent bonds. You'd have to break those bonds. Okay, how about NH3? NH3, nitrogen has 3 bonds available. That's 1, 2, 3. And that's going to be all filled up with H's. Okay, well, then that's also going to be molecular. But we've got the N to H bond here, so that's going to be hydrogen bonding. All right, so we've got hydrogen bonding, HBs, then molecular. Okay, how about aluminum chloride? Well, this, aluminum is going to be a 3+ charge, chloride is going to be a -1 charge. So aluminum chloride is going to be an ionic. I've totally abandoned the colors here. Let's be consistent, Chesky. And it's going to be a +3 to -1 charge. Let's keep that in mind. Okay, then KCl, again, this is going to be ionic. And it's going to be a +1 to a -1 charge. All right, then helium. Helium's not going to bond with anything else, so it's going to be just sticking together with London dispersion forces, LDFs, and it's going to be an atomic solid. All right, there we go. So we've labeled all these. Now we can come back and figure out which of the above substances are molecular. Well, we already figured that out. We've got CCl4 and NH3. And we could say helium, but we're not gonna. I'm gonna prefer that's atomic. So we've got CL4, and NH3. Let's move that other way. Okay, what else? Which of the above substances is an ionic bulk crystal? Okay, so really just what's an ionic solid? That's going to be AlCl3 and KCl. All right. Which of the above substances is network covalent? That's going to be SiC. It's going to be silicon carbon. Now this would have a specialized name, especially depending on what our ratio between these two would be. Which substance here is likely to have the highest melting point? Ooh, that's going to kind of be a toss-up between silicon chloride and silicon carbon and aluminum chloride. The reason for that is that this SiC is going to have to break a covalent bond in order to melt. And this ionic solid is going to have to break an ionic bond in order to melt. Those can overlap. We can see those overlap sometimes. However, we know that if ionic is going to beat this particular bond, then it's going to be this one, not this one, because this has a bigger charge. Okay? Which substance is likely to have the lowest melting point? Well, that one should be obvious. That'll be helium. Because helium is going to be small. Both of these, both helium and carbon tetrachloride, both are only held together with London dispersion forces. But because carbon tetrachloride has so much more going on with it, it's going to have a lot more mass, a lot more volume for those London dispersion forces to activate. It's going to have a much higher boiling point or melting point than helium. Helium has a melting point close to 1 Kelvin. Very, very low. So which substance is most likely to be a gas? Come on, Schweitzer. Okay, which substance is most likely to be a gas? Helium. And at room temperature, we know it's a gas. Which will have the higher melting point? AlCl3 or KCl? Well, we already explained that up here when we established that it's going to be this one or this one with the highest melting point. So we know it's going to be AlCl3 because bigger charge. Ammonia at room temperature can be a liquid, whereas both N2 and H2 are both gases independently. Draw a Lewis structure of NH3, N2, and H2. All right, well, NH3, H2, and N2. It's going to have triple bonds here. Okay, there we go. What about NH3 makes it a liquid? Well, the difference between these is H2 and N2. The only thing holding those together are going to be London dispersion forces. They're not even polar. So this one has hydrogen bonding. So there is a much larger force holding this together. It'd be like, I think it's 40 times the force that could hold this together. So NH3, what makes it a liquid? Hydrogen bonding. All right. A local farmer's dog has died unexpectedly. Oh no, that's terrible. And he thought his dog may have been poisoned. A common poison to dogs is ethylene glycol, C2H6O2. Ethylene glycol is commonly used as antifreeze. It has an unusually sweet taste, and animals can inadvertently drink it. What is the percent mass of each element for this compound? Well, C2H6O2. What's the molar mass of that whole thing? Let's grab a calculator. Right here. Okay. I know carbon is 12. So it's going to be 12 times 2 plus hydrogen is 6, so plus 6, plus an oxygen is 16 times 2. And that gives us a total molar mass, can you see that, of 62. So 62 grams per mole. So then the carbon at 12, the hydrogen at 1, and the oxygen at 16, we can figure out each of these molar masses, or percent masses, sorry. So carbon is going to be 12 times 2 divided by 62. We'll give ourselves some room there. Hydrogen, there's going to be 6 of them, so it's going to be 1 equals 1 times 6 of them divided by 62. Then oxygen equals, I'm just messing this up. Oxygen is going to be 2 oxygens times 16 for each one divided by 62. Okay, let's punch those in. So carbon, 12 times 2 divided by 62. That's going to give me 0.387, so it's going to be 38.7%. Hydrogen, that's going to be 1 times 6, I could have just put in 6, divided by 62. That's going to be 0.096, so 9.6%. Okay, and then oxygen, 2 times 16 divided by 62. That's going to be 0.516, so that's going to be 51.6%. Don't mind my calculator, I have it in engineering notation, it's fancy, whatever. Okay, so these are our percent masses. Okay, a chemist analyzed the animal and found it to have an unusually high concentration of a chemical that is 27.27% C and 73.7% O. Well, that's not going to be that stuff. Okay, well, what would be the empirical formula of this substance? Should the person dismiss this chemical? All right, well, let's look at it. So carbon, let's divide this out so that we have some working area here. Carbon, actually, I'm gonna break this out. So carbon is going to be at 27.27%, and oxygen is going to be at 73.7%. Okay, so I've got these two. So I want to figure out what the empirical formula for this substance is. So first thing I'm going to do is go, well, the whole thing, just sample size of 100 grams. So carbon is 27.27 grams, and then I need to convert it to moles. So it's going to be 27.27 divided by 12 grams per 1 mole. And then oxygen is going to be 73.7 times the 16 grams per 1 mole of oxygen. Let's punch that into our calculator. It's going to give me 2.27 moles. Okay, and then 73.7 divided by 16. That's going to give me 4.6 moles. Okay, so now 2.27, 4.6. All right, 2.27. Oh, sorry. We're going to divide by 2.27. Both of them. 4.6 divided by 2.27, and that's going to round out right to about 2. So the empirical formula of this is CO2. Okay. Let's move this up. Got some stuff in my way over here. So that's going to be CO2. Should the person dismiss this chemical? Well, large amounts of CO2 can cause CO2 poisoning, so no, they should not dismiss this chemical. Okay, the molecular weight of this unknown compound is 88 grams per mole. What is the unknown substance? Okay. All right, CO2 is going to be 12 plus 2 times 16. It's going to be 44. All right. The molecular weight of this is 88 grams per mole. We're coming out with 44. So 88 divided by 44 equals 2. So we need to multiply this whole formula by 2 to get our actual correct formula. So it's going to be C2O4. So a quick internet search should tell you that this C2O4 is oxalate. C2O4, there's a hole, oxalate. Oxalate can be poisonous if it is consumed in high quantities. Likely, it was poisoned. It's very difficult to consume too much oxalate normally. There we go.